Let's visit Hardy-Weinberg. Hardy-Weinberg equilibrium, sometimes called Hardy-Weinberg equation, allows population geneticists to compare genotypic and allele frequencies in a given population over time. It has to meet 5 rules, though, in order for it to be considered in equilibrium. There cannot be any gene mutations. There can be no migration. The mating will be random. No genetic drift and no natural selection. So let's just be honest. This never occurs in nature because there's always at least one rule being violated. But it is an ideal state and a baseline that allow those geneticists to be able to predict allele and genotypic frequencies of future generations, genotypic and allele frequencies, assessment of current population, and to interpret those of earlier generations. And so that is the significance of what this equation explains. There are 2 equations, and in an effort to explain how it's derived, let's look at this example. So we have a population before the Industrial Revolution with 3 different genotypic frequencies of moths. We can see that for the darkly colored moths, there are only 4% in the population, so 0.4. And that makes sense because we're talking about before the Industrial Revolution. For those that are heterozygous, that are still going to be dark, we're looking at that making up 32% of the population. And for those that are white, they're going to make up 64% of the population. And that pretty much makes sense because of the environment before the Industrial Revolution. So if we want to kind of look at what that looks like as far as allele frequencies, if we want to look at the dominant allele frequency, then we can see that the dominant allele frequency for homozygous dominant was 4%. But also know that in the heterozygous condition, half of those alleles are of the dominant type. So if 32% of the population, that's going to be 16% are going to represent the dominant allele. And so when we add that together, the dominant allele is going to be represented inside of this gene pool at 20% of the time. If we want to look at the recessive allele, we can see that the recessive alleles represented 64% of the time. But remember, the other half of the heterozygous condition, or 16%, is going to represent the recessive allele. So when we add those together, that's going to give us a recessive allele frequency of 80%. So if I had a cup of beads, I would have 20 beads that are red, and I would have 80 beads that are white. That is telling you the allele frequency. The allele frequency. And when we are talking about Hardy-Weinberg, we assign the value P for the dominant allele frequency and Q for the recessive allele frequency. And if we look, P plus Q must always equal 1. Okay. So that allows us to look at allele frequency. Now that we have allele frequency, we can now use those values in order to find genotypic frequency. And so when we are talking about homozygous dominant, when we are talking about the heterozygous condition, and when we are talking about the homozygous recessive condition, then we can use these values to come up with our second equation. And our second equation is going to be the use of these values. So here I'm going to have a P and a Q for my heterozygous condition. Remember, I could have a big D little d, or I could have a little d big D composition. And so that then is going to write our second equation as such. This again will also equal to 1. So that allows us now to use the allele frequency and the genotypic frequency to solve problems like what are on your worksheet. So if you'll now grab your worksheet, you should be able to find the information asked on the worksheet based on these two equations. And so let's do the first one together. Okay, I hope you've had some time to grab your Hardy-Weinberg practice worksheet. If you want, you can stop the video and catch up. I'm going to want you to catch up on your worksheet at number 4. So if you want to go ahead and pause the video and then do questions 1 through 3, that would be great. Okay, welcome back. Now we're on question 4 of the worksheet. On question 4, it says if the frequency of the recessive allele is 20% or 0.2, what's the frequency of the dominant allele? So what they have given you is Q, and Q equals 20%. They're wanting you to find P, and P is going to be 1 minus Q, and that is going to give you a value of 80%. Okay? Now, number 5, we want to find the frequency of a genotypic calculation. So if the frequency of the homozygous dominant genotype is 0.36, so let's just make a homozygous dominant phenotype, and it's telling you that value is 0.36, now we're going to use our p squared plus 2pq plus q squared equals 1 in order to register this data. And what they have given you is p squared. They have given you p squared. So in order for us to solve for p, we're simply going to take the square root of that 36%, 0.36, and that's going to give us a p-value of 0.6. They also want to know the Q value. So now that you've found the P value, the Q value is going to be 1 minus the P value, 0.6, and that's going to give you a P value of 0.4. Remember, P plus Q must equal 1. Okay, let's do number 6. Number 6, 2% of the human race has red hair. So if we're talking about hair color, and they've given you the homozygous recessive of 2%, those are my gingers, what percentage of the population then is heterozygous? So this is what we're aiming to try to find. Now we're going to use our equations to go backwards and forwards in order to be able to solve for this problem. So what they've given you is Q squared. Q squared is 2%. To find Q, we're going to take the square root of that, and that is going to give us a Q value of 0.14. That's going to allow us then to find the P value, which is 1 minus Q, and the P value then is going to be 0.86. We know that the equation for finding heterozygous conditions is going to be 2pq. So now we have 2 times 0.86 times 0.14, and that gives us our final value of 0.24 or 24%. So 24% of the population is heterozygous. From there, we could find the homozygous dominant as well. But that's how you apply Hardy-Weinberg. And that is how you are able to work through these problems and look at the evolutionary data on a baseline scale for a population that is not evolving, which is not natural. But it allows you to be able to apply both equations in order to calculate the allele frequency and the genotypic frequency.